Sequential fuel injection systems. Sequential fuel injection systems control each injector individually so that it is opened just before the intake valve opens. This means that the mixture is never static in the intake manifold, and that adjustments to the mixture can be made almost instantaneously between the firing of one injector and the next. Sequential firing is the most accurate and desirable method of regulating port injection. In sequential fuel injection systems, each injector is connected individually into the computer, and the computer completes the ground for each injector, one at a time. In multiport injection systems, the injectors are grouped, and all injectors within the group share the same common ground wire. Central multiport fuel injection. In the central port, or central multiport fuel injection system, a central injector assembly is mounted in the lower half of the intake manifold. The system uses one injector to control the fuel flow to 6, or on 6-cylinder engines, individual poppet nozzles. The system injector assembly consists of a fuel metering body, pressure regulator, one fuel injector, 6 poppet nozzles with nylon fuel tubes, and a gasket seal. The injector distributes metered fuel through a 6-holes distribution gasket. The gasket seals the injector to the 6 lines connected to the nozzles. Each nozzle contains a check ball and extension spring that regulates fuel flow. The poppet nozzle opens when high pressure is exerted on the check ball. This action allows the nozzles to feed individual cylinders with atomized fuel. Gasoline direct injection systems. Direct injection has been around for many years on diesel engines. Until recently, this type of injection system has been seldom used with gasoline. With gasoline direct injection, the gasoline is injected directly into the combustion chamber. GDI allows for very lean operation, as much as 35:1, during cruising. When the engine is operating under heavy loads, the system provides near stoichiometric air-fuel ratios. Because the engine is able to run at such lean ratios, its fuel economy is increased by nearly 30%, and the emission levels are substantially decreased. Spraying the fuel directly into the cylinder also increases volumetric efficiency, and allows for higher compression ratios, without the need for higher octane gasoline. These features result in increased horsepower and torque outputs from the engine. The fuel highly pressurized up to 10,000 kPa when it is sprayed into the cylinder. Under this pressure, the fuel arrives as a vapor. The fuel injectors are specially built to be able to close against this pressure. The fuel pump that delivers this high pressure to the fuel injectors is driven by the engine. The pump is fed by an in-tank electric fuel pump. A powertrain control module controls the timing of the injection and ignition for each cylinder. Although GDI offers many advantages over port injection, there is concern about the NOx levels produced by the engine. Because of the very lean air-fuel ratios and the high compression ratios, combustion temperatures are very high during highway cruising. There are other concerns as well, but it is likely that there may be more GDI engines on the road in the future. Input sensors. The ability of the fuel injection system to control the air-fuel ratio depends on its ability to properly time the injector pulses with the compression stroke of each cylinder, and its ability to vary the injector on time according to changing engine demands. Both tasks require the use of electronic sensors that monitor the operating conditions of the engine. Many of the same sensors used with computer-controlled carburettors are used with electronic fuel injection system. Airflow sensors. In order to control the proportion of fuel to air in the air-fuel charge, the fuel system must be able to measure the amount of air entering the engine. Several sensors have been developed to do just that. Volume airflow sensor. The airflow sensor, or commonly called an airflow meter, or vane airflow sensor, measures airflow, or air volume. The sensor consists of a spring-loaded flap, potentiometer, damping chamber, backfire protection valve, and idle bypass channel. As air is drawn into the engine, the flap is deflected against the spring. A potentiometer attached to the flap shaft monitors the flap movement, and produces a corresponding voltage signal. The strength of the signal increases as the flap opens. The signal voltage is relayed to the electronic control module, and may be used to control the fuel pump. The curved shape of the airflow sensor is the damping chamber. The damping flap in this chamber is on the same shaft as the airflow sensing flap, and is also about the same area. As a result, the damping flap smoothes out any possible pulsation caused by the opening and closing of the intake valves. Airflow measurement can be steady signal, closely related to airflow as controlled by the movement of the flap. The airflow sensor flap provides for backfire protection with a spring-loaded valve. If the intake manifold pressure suddenly rises because of a backfire, this valve releases the pressure and prevents damage to the system. The airflow sensor assembly includes an extra air passage for idle, bypassing the airflow sensor plate. When the throttle is closed at idle, the opening and closing of intake valves can cause pulsation in the intake manifold. Without the idle bypass, such pulsation could cause the flap to shudder, resulting in an uneven air-fuel mixture. The idle bypass smooths the flow of the idle intake air, ensuring regular signals to the electronic control. Karman Vortex. Another design of airflow sensor, called a Karman Vortex sensor, work on a different operating principle. Air entering the airflow sensor assembly passes through vanes, arranged around the inside of a tube. As the air flows through the vanes, it begins to swirl. The outer part of the swirling air exerts high pressure against the outside of the housing. There is a low-pressure area in the center that moves in a circular motion as the air swirls through the intake tube. Two pressure-sensing tubes near the end of the tube sense the low-pressure area as it moves around. An electronic sensor counts how many times the low-pressure air is sensed. The faster the airflow, the more times the low-pressure area is sensed. This is translated into a signal that indicates to the combustion control computer how much air flowing into the intake manifold. Air temperature sensor. Cold air is denser than warm air. Cold, dense air can burn more fuel than the same volume of warm air because it contains more oxygen. That is why airflow sensors that only measure air volume must have their readings adjusted to account for differences in air temperature. Most systems do this by using an air temperature sensor mounted in the induction system. The air sensor measures air temperature and sends an electronic signal to the control computer. The computer uses this input along with the air volume input in determining the amount of oxygen entering the engine. In some early electronic fuel injection systems, the incoming air is heated to a set temperature. In these systems, an air temperature sensor is used to ensure that this predetermined operating temperature is maintained.